switch.
Can everyone see me?
Okay. So.
Do you have a screen that displays this, or is this on your computer?
This is on my computer.
Okay.
So actually you're live. So basically you can start whenever you want.
Okay.
I'll just hide myself.
Perfect. So welcome everyone. I can't see you, but still saying hi. Today I'm going to give a talk about consensus algorithms. So before I begin the talk, I noticed one thing. So whenever I gave the talk, people would ask questions in the middle, but I noticed that usually the answer of the question is answered in a later slide. So I would appreciate so much if you could just all ask questions at the end. And please let me know if you have trouble hearing me, or if there's any latency issues we can adjust along the way. And full disclosure, I'm an awkward person. I like to make a lot of jokes, but not all people don't always get my joke at the right time. So to do you all a favor and to do myself a favor, I have this phone with me. I have an automatic soundtrack that I would press when I think when I'm making a joke. So basically, if I press the button, if it laughs, I would appreciate if you laugh along. So let's start the talk. I'm going to share my slides. Let me know if you have trouble seeing it. So I'm going to click screen share. Wow, look at that. Okay, so I'm going to switch to preview. Let's see. Enter full screen. Okay, let me know if anyone have problem seeing the slides. Okay, so welcome to the consensus algorithm talk. Well, I promised Avadas that I would talk about consensus algorithms, but I actually lied. So let's talk about cakes. Are you able to hear that laugh sound? That's a practice run. Okay, I can't hear any of you. So I'm just gonna pretend that you heard it. So, let's start by having a poll. I'm going to switch back to this poll. Can everyone see this? I hope so. So I'm gonna, if you could pull up your phone and enter this event code called Slido. And if you can join the poll, enter G559. I would really appreciate if you participate. And Alvadas, I can't really see if people have trouble joining the poll. So if everyone could just look up once you're done joining the poll. And Alvadas, you can tell me if we can move on. Are we all good? Okay, everyone join the poll?
Yeah, everyone saw the slide.
Perfect.
Okay.
So I picked a Christmas background. So I want to wish everyone a happy holiday. So let's just go ahead and start. So now I hope you can see the questions. And so the first question is it difficult for you to choose between a chocolate cake or a cheesecake? So for me, it's so ridiculously hard. I never know which one to pick. And let me know, Alvadas, please tell me whenever people are done answering the results. I am watching the results from my end. I can see it was 50-50. Oh, wow. Oh, by the way, you can change your answer in case if you change your mind. So let me know if everyone is done. Okay, so I think I'm looking at 59% saying nah, it's easy, and 41% it's yes. Okay, I'm already friends with the 41%. Okay. Has one? Okay, 39%. Wow, the yes keeps dropping. That is a little sad because I was hoping yes could, could have more difficult than not. It's easy because, this talk won't really work if it's easy for you to pick between a chocolate cake or a cheesecake. Okay, everyone answered the question? Can we move on to the next question?
Yeah, I think so.
Great. Okay, so the next question is, have you used any software/libraries that relies on distributed system? So when we talk about softwares and libraries that relies on distributed systems, that means, email basically counts, right? And the web browser. Basically, have you ever been online before? Which I'm expecting 100% yes. Oh no, we have 7% no. Oh no. Slido, what you're using right now is probably using some distributed system service, by the way. So if you're answering no, you can still change your answer right now. Okay. Okay, so we have about 95% of yes and 5% no. Okay, let's move on. Can you describe the details of one of the algorithms used in any distributed systems? And when we talk about the details of a consensus algorithm, basically that means can you can you explain how it works, why it works, and give examples of where it's used? Let's see. And if you do know any details of the consensus algorithms, please shout out the name. I won't be able to hear you, but I'm sure Alvidus can tell me. Okay, I'm seeing so far nobody has said yes yet. Okay. Vaguely, and then no, and then nobody said this is easy. Okay. I'm waiting for 2 people who's still answering the question. Okay. Now we have 1 more person. Oh, yay. Okay. Cool. So nobody answered absolutely. So if you take a look at the poll results, most people, 95% of the audiences have used the software or libraries that relies on distributed systems, which is, but only a few of us, actually, none of us understand how to describe the details of the consensus algorithm that used underneath the distributed system. So the goal of this talk is to help everyone to understand how consensus algorithm works and how, in a distributed setting, how computers reach consensus and how they work together. So we don't want to just use the service. We want to be able to understand how they work, right? So let's just quickly switch back to the slides. Let's enter the full screen mode. Okay. So let's first define what is distributed system. You can think of them as components located on different parts of the machine, and they communicate with each other by sending messages to each other. So some modern examples of a distributed system would be the web. So when you're using the browser, you can think of the web browser as the client and the central server as, the web server is the central server. So this is an example of a distributed system. And also DNS server. So when you're using your browser, when you put a link in your web browser, it's going to look up the DNS server and find the IP address associated with the host name, and it's going to direct you to the right place. And also BitTorrent is an example of a distributed system. So BitTorrent, we use that for only Linux distribution, right? None of us actually use it for downloading movies or streaming music, I'm sure, but it's an example of a distributed system. So fun fact, in 1920s, American Airlines has this central office where they used to have a deck of cards and 1 card for each flight. So they would mark the seats sold as sold on the card. So the traveling agent would call in the central office asking, hey, I want to purchase the seat. Can you tell me if the seat has been sold or not? So the people who work at the central office will look at the card, and if it's not been sold yet, it will sell the seat to the traveling agent, and then it will mark it as sold. So this is a very early example of a distributed system. So distributed system is really helpful, and it's really hard to get around without using a distributed system service. But also distributed system has its own challenges. So first of all, we said each machine, there are components located on different parts of the network, and they exchange information by sending each other messages. But when they're exchanging messages, how can we make sure that the information is up to date? How do we detect inconsistencies? Remember that there are components located on different parts of the network. That means no computer has a global knowledge of everything. Another challenge, since we're talking about different machines, it's possible that they have their own clock skews. So how do we deal with delayed messages? How do we deal with duplicate messages? How do we know the order of the messages that we received? Well, another challenge would be, since we're dealing with a distributed system, it's very possible to have multiple concurrent operations on one single object. So when this happens, how do we ensure that the object is in a consistent state? How do we detect conflicts? So Leslie Lamport has mentioned that a distributed system is a system where some failure of other machines, you didn't know where that machine is, that could render your computer unusable. So obviously, the failures of other machines would affect us. So how do we tolerate the failures of ourselves and other machines? By tolerate, we mean how do we detect the failures, how do we handle them, and how do we recover from them? But so fortunately, we have consensus algorithm that could help you to protect the integrity, the reliability, fault tolerance, and availability of your machine. So today we're going to focus on two consensus algorithms, Paxos and Raft. So we can start from Paxos, and Paxos has a really colorful background compared to the other consensus algorithms. So it was first, the idea came up by Nancy Litch and Barbara Liskov. First, when they designed the algorithms, mathematical proof weren't provided in the paper. So Leslie Lamport one day found this paper, and he was looking at this paper. He had a very malicious thought. He said, I'm going to prove this paper wrong. And by the way, Leslie Lamport, if you happen to watch this streaming right now or in the future, please don't be mad, because I learned all these from my professors. You should just be mad at my professors, not me. So after he found this paper, he wants to prove it wrong, but he accidentally proved it right. And so he wrote this paper called The Part-Time Parliament, which had a very long and complicated story about the Paxos Island and how they work together. However, the paper was rejected because it was too complicated that people had a hard time understanding what Paxos is. And he tried about 10 years and eventually got it published. So one day he was at a conference and people were asking, Leslie, we can't really understand the Paxos algorithm in your paper. Can you just please explain to us how it works? So he sat down with people. He didn't mention the fancy Paxos story and the Greek names in the story. He just sat down and simply explained the algorithm. And people understood. So he was very inspired. He went home and wrote this paper called Paxos Made Simple, which basically is basic Paxos algorithm without the story, the complicated stories. So he published this paper, and then later he published another paper called Multi-Paxos, which is basically Paxos and complexity, which today we'll talk about both. So let's start with basic Paxos. Actually, strike that. We're going to talk about cakes first. So don't think about Paxos. Let's just think about how do we achieve consensus as a group. So consensus means as a group, we want to agree on one value, right? Let's say after this meetup, we're going to go out and buy one cake. But we have to choose between chocolate cake or cheesecake. So have to choose one flavor among the 20 people of us. And now, what do I usually do? How does this usually work? Well, you can imagine that usually if someone raises his hand or her hand saying, oh, as a group, have we picked a value yet? And then people will respond, no, not really. I don't think we decided on what to pick. And then the original proposer will say, why don't we just go for cheesecake? We can't be wrong with cheesecake. And the other people would usually respond, okay, well, sure, why not? Let's just go for cheesecake. And this is actually Paxos. So in Paxos, we have this proposer, which proposes a value, and also the idea of an acceptor who is responsible for accepting and rejecting values. So let's walk through the steps. In basic Paxos, we start with the original proposer. The original proposer, the machine will always choose a proposal value first. So the machine will choose a number n that is the largest it has ever seen. And this is basically the step where we have one person in the group asking, has anyone picked a flavor yet? And then the proposer will broadcast this number to all of the servers by sending out this prepare message. It's going to say, hey, other servers, I'm trying to propose a value. And now the other servers will see this message, and basically they will make a decision by looking at this value. They will check, is this number n the largest proposal number that I've ever seen? If that's true, we're going to update the max proposal number to be n, and we're also going to respond a promise to the original proposer. So that means we're going to say, I promise you that I will not accept other proposal numbers unless their number is larger than yours. So basically, this is the group responding the person, I don't think we've ever chosen a cake flavor yet, so go ahead and pick a flavor. And now the proposer will get the votes, and it will count, did I get the majority of the votes from the machines? If it receives the majority of the votes, it will just say, okay, now I understand that I can go ahead and propose a value. So it will send out this accept message that has two things. It has the original proposed value, proposal number, and it will also have the proposed value. So basically, this is the step where the person says, let's go for cheesecake. And now it will broadcast this message, and it will the other machines acting as acceptors, they will check, okay, is this value still the largest proposal number that I've ever seen? Basically, it's trying to see, is this the same proposer that is proposing a value? If that holds true, then we're going to finally accept this value, and we're going to respond to the proposer. So now the proposer will check, have I gotten the majority of responses? If that's true, if I've not gotten any rejections yet, that means my value is chosen. But if I get any machine rejecting my value, that means my proposal number is not the largest. That means we're going to have to restart from the beginning. Basically, if our value is chosen, then that means we've chosen cheesecake, and we can go ahead and enjoy the cake. And I know you can't see me right now, but I'm gonna drink some water. So sorry about a few minutes of silence. Okay, so we've been talking about the proposal number in Paxos. What does it mean, and what do you mean by the largest proposal number? So usually the proposal number is formed by two things. It's formed by server ID, which guarantees the uniqueness of the proposal number, and also a round number that gets incremented over time and is shared among all the servers. And we always remember the highest round number. So to generate a new proposal number, you increment the max round number and concatenate it with the server ID. That's how you generate that proposal number. So that was basic Paxos, and it's fairly simple, right? It's not as difficult as what's in the paper. So let's now take a look at a multi-Paxos. So you can think of multi-Paxos as a sequence of instances of basic Paxos, and it works around log entries. Here's how it works. So we have a client who want the cluster of servers to process some requests, right? So the client's going to send a command for the server to execute, and the leader will receive this command. So it will use basic Paxos to reach consensus among all the servers, trying to pick which command to execute for the current entry. And now once they've decided that, they will make sure all the commands in the previous log entries are applied, and then it will also apply the current log entry. And now, once the leader gets a result, it will send back the results to the client. Now, that's how multi-Paxos works. So in multi-Paxos, we have this leader and non-leader thing. So leader in the multi-Paxos is a distinguished proposer. It's the server with the highest ID and is responsible for sending heartbeat to other machines for every t milliseconds. Or this t milliseconds is basically the time interval that the other servers are waiting after receiving the last heartbeat. So the leader is also responsible for accepting requests from the client. So as a non-leader, as a follower, if you didn't receive heartbeat for a period of time, then you just assume that the leader has died or is down. So you're going to step up as a leader and step up as a proposer. But if everything works right, if you continue receiving heartbeat from your leader, you will just redirect client request to your leader and act as an acceptor. So in Paxos, it's very unlikely that we will have two leaders at the same time because of how proposal and the proposal phase works. But it's designed to be able to handle multiple leaders. However, if you have multiple leaders working, it just won't be efficient as having just one leader because of the constant conflicts that you have to deal with. Some of the industry examples of Paxos would be Google Chubby, the log service, and also Apache Zookeeper, which uses Paxos-like algorithms to provide distributed system services for the other services. Paxos algorithms or Paxos-like algorithms are used widely in the industry. Okay, let's talk about Raft. That was Paxos. I hope that was a understandable or fairly simple introduction of Paxos. So Raft, let's again start with the background. Raft was designed by Diego Ongaro and John Osterhout at Stanford. People recognize Raft as a simpler version of Paxos. So when we talk about a simpler version, it doesn't mean that it's easier to implement or easier to work with in general. It just means that the original paper has more information and more details, so that it's simpler for people to understand and to understand why it works and to understand how to implement it. In terms of performance and fault tolerance, is equivalent to Paxos. And on top of consistency and correctness and conciseness, Raft work also is designed around understandability. So let's take a step back and think about why, when the professors designed Raft, why did they paid a lot of attention on understandability? So in the industry, as developers, when we implement consensus algorithms, when we use services integrate them into our own systems, we want to be able to understand how the service or the library works before using them, right? So sometimes we even have to twist the libraries a little to be able to extend them and adapt them to our own environment. So in that scenario, when you're designing an algorithm, you want people to be able to understand your algorithm so that they feel confident of using it and they can twist it or change it to adapt to their own system. So most algorithms are pretty hard, or most consensus algorithms are pretty complicated. So you really want people to be able to understand it before go ahead and using it or make a mistake when it's like hard to debug. So that's why understandability was definitely one of the focus when designing Raft. So Raft, different from Paxos, it works around logs. And let's talk about cakes again. So Avidus, I need your help. Could you just randomly pick an audience? I need a volunteer from the audiences. I can't see any of you, but can you just shout out the name of the person who's volunteering? I just need a name of the person.
Volunteers? Do you have any volunteers? Raise your hand. So far, no volunteers. What do you exactly mean? Want?
Just pick someone. Give me a name. I just need your name.
Can you come? Okay, can I give you a name? No? No? Okay. Okay. I have a volunteer. I can tell me your name. Olga. We have
Say that again.
Olga.
Olga?
Yes, yes.
Olga. Okay. So let's say as a group, again, we're going, after this meetup, we're all going out and we're going to pick a flavor between buying a chocolate cake and a cheesecake. Now, Olga in our group, we're going to choose Olga as the leader who's going to pick a cake flavor. And so Olga, pick a flavor between chocolate cake and cheesecake. Chocolate cake. You pick cheesecake. Okay, fine. So yay. Okay, so now because we chose Olga as a leader, we are going to follow Olga because we know that Olga is the best among us to pick a cake flavor. And Olga picks cheesecake. So now we have a consensus among all the people because we just followed Olga. Okay, so as a group, we've reached consensus. And this step basically is Raft. So now I'm going to talk through how Raft works. So in Raft, we have two phases. One is we'll start with a leader election. So this is the phase where we elect one machine to be the leader. And during this leader election phase, basically, if we detect the previous leader, if the leader crashed or something happened, we're going to re-elect the leader. So this is the phase where we elect Olga to be the leader among the group. And the second phase is called the log replication. Basically, this is when we have the leader process commands from the clients, and also as followers, we replicate the logs from basically to copy the leader's logs. And this is where we guarantee the consistency and consensus among the servers. And again, this is the phase where, as a group, we're listening to Olga and saying, okay, whatever flavor you pick, we're just gonna go ahead and listen to you. Okay, so let's look at the first phase, leader election, how it works. First of all, one machine will time out and become a candidate. So after, each server will have its own timeout time, and it's ranged randomly between 100 to 300 milliseconds. One machine will time out first, and it will become candidate, and now it will want to become a leader. So it can't become a leader yet. So what it will do is it will increment its own current term. it will just say, okay, so the current term is keeping track of how many election phase we've run through. So it's going to increment the election phase, because now we're in the election phase again, and now it's going to vote for itself. So now, after it's done voting for itself, it's going to send a request vote remote procedure call to the other servers asking, can you please vote for me? And now 3 scenarios could happen from here. So after send out this request to the other servers, if the original candidate has received the majority amount of votes, it's going to become a leader. I wonder if you can see my mouse, because that's a lot easier, because I'm pointing at the place that I'm talking about to make sure you understand what I'm talking about. So after it's received the majority amount of votes, it's going to step up and become a leader. And then it's going to send heartbeats to the other servers, and is also going to handle requests from the client. So basically now, after we've have one leader elected, that means we've passed the election phase. Well, there could be another scenario where we received a heartbeat from the legit leader. That means someone during the election phase has become a leader first before we did. Now, we understand that there's already a leader in the system, so we'll just step down as a follower, and we're going to redirect client request to the leader, and we're going to enter the log replication phase. And then there's a third scenario, which is called the split vote scenario, where we have a timeout. We'll get into more details later. So how do we really make sure that election works? In Raft, we guarantee that we only have one leader per term. Basically, we only let one server to vote once per term, and whoever gets the majority amount of vote will win the election. And how do you calculate the majority amount of vote? So it's the total number of machines divided by 2 plus 1. So let's look at this example down here. So let's say we have 5 servers, 5 nodes, right? Sorry, 5 machines, 5 nodes. So let's say server 0 and 2 and 3 all votes for server 0. And server 1 and 4 both votes for server 1. And in this case, we understand which one will be elected as a leader, right? Because server 0 received the majority amount of vote. So now server 0 will be the leader. So now this explains why we only have one leader per term. Okay. So also Raft guarantees that there will be eventually a leader exist in the distributed systems, because again, we mentioned each server has its own random election timeout. The random election timeout time is assigned to each server, and it's ranged between 100 to 300 milliseconds. And of course, you can change this number, the range, to adapt your own system. And usually one machine will have the shortest timeout time, so it will time out first, and then it will win the majority amount of vote. And usually this machine will become a leader. But if 2 machines, let's just say they time out at the exact same time, and this scenario is very uncommon, but it's possible, right? So in this case, now we have this split vote scenario where the 2 machines, they just happen to get the same amount of votes. So now what happens is that we'll also have this election timeout time. So after waiting for a period of time, no leader has been elected during election time. Now all the servers will just time out, and then they will re-enter the election state. So that means we start from the beginning, right? So we start from the beginning by incrementing the term again, because we're entering to another election term. And now we're going to get random timeouts among the servers, and also we are, again, going to gather votes from the other servers. So it's restart the process. And now that was a leader election for Raft. So again, the first phase is passed. Now let's talk about the second phase, log replication. So the log replication phase looks like this. Now we have one leader elected, right? Because after we passed leader election phase, we assume that there's already a leader exist in the system. Now we have one client that will try to send us requests that would want us to work for it. So the leader receives the request, and it will try to do this first. It will try to append this command to its own log. So we'll basically try to log whatever the client wanted to do. And now the next step is to send a message to the other servers, sending this append entry remote procedure call to the other servers saying, hey, could you please also append this log entry to your own log, because our client wants us to do this. So the other servers will receive this message, hopefully, and they will append this entry to its own log. And now it's not done yet. It's going to reply the server a acknowledgement saying that I've received your message and I've done what you asked me to do. So now if the leader gets a majority of servers responding to its message, so basically if it receives the majority of acknowledgement, it can do three things. One, it can commit this entry. And so by committing an entry, basically it means it's safe to execute the entry. So it's going to go ahead and execute the command in the log. And now it's going to return the results to the client, because the client shouldn't wait for longer after having consensus among all the servers. And now you think it looks like it's done, right? But hold on, we have one more step to go. So now, after the server has committed this entry to its own log, it has to ask the other servers to do the same. So now it's going to send out this, again, append entry RPC again to the other servers. And the other servers, after receiving this request again, is going to commit this entry to its in its log. So it's going to just repeat what the leader has done. And now that just concludes Raft. So this is how Raft works, how log replication works, if everything works really well. But what if there are problems during this log replication phase? It sees, as you can see, we have a lot of communication over the network going on. So let's just say during the log replication process, if the server wants the other if the server wants the other followers to log this entry to its own log, if it didn't receive the majority of responses, basically didn't receive the majority of acknowledgements, so what happens? So in this scenario, as you can see, the server asks the other followers to say, hey, could you please append this command to your own log? And now let's just assume that all the other messages dropped, but except this one, except the second one. So this second blue node received its message and it append the command to its own log and send back an acknowledgement. So now, as you can see, that our server did not get the majority of the other nodes responding to it, right? So because we have 5 servers in total, we only got 1 acknowledgement. So that's not majority. So that means we're not succeeding. And in this case, the leader will just keep trying. It will just retry, keep sending those messages to the other server until it gets the majority of responses from the other server. So it simply won't give up. And let's take a look at what the logged entry look like. So for Raft, the log entry contains 2 things. It has the term the log comes free with an index, right? But it has the term which keeps track of the current term when receiving the command. So that, remember the term that we keep track of during leader election, that this is the same number. Also the command. So this is the command from the client that the client wants us to execute. So how do we, obviously server crashes when service could crash during log replication. How do we make sure the log is consistent? And how do we first detect inconsistencies? How do we maintain consistency during log replications and leader election? So now this is an example of log inconsistency. So as you can see, I drew 3 servers, right? So server 0, 1, 2. And now you can see that server 1's log is so much shorter than the other servers. And this is basically a inconsistency because server 1 might crash or be partitioned out, or did something happen during the 2 phases, and now it has a shorter log than 0 and 2. So this is an example of log inconsistency. So how do we detect this, and how do we fix it? So to fix log inconsistencies, we basically do 2 things. Remember, we said there is a log replication, the leader election phase. So first of all, during leader election phase, we do not elect a candidate with inconsistent logs because we always trust the leader's log. Because of that, we have to guarantee that the leader we elected has the most up-to-date log. And we also guarantee that during append entry or log replication processes, we guarantee that there's no holes in the log. Basically, it means we do not skip entries. We always append to the next empty entry in the log. And that holds true for all these servers, for all the leader and followers. So also during log replication process, we repair inconsistencies, and we'll talk about these later, how we repair inconsistencies. So first of all, let's take a look at how do we guarantee the leader's log completeness during leader election phase. So remember that during leader election phase, one candidate will request the other servers to request vote. So basically, it wants the other servers to vote for the current server, and it's going to send out this request vote remote procedure call, which contains the 4 following items. The first one is the term. So this has the current candidate's term, and again, this is keep track of how many elections we've gone through. And it's also going to keep track of the candidate ID. So who am I? What's the ID? Who I'm voting? Who was my current ID? And also, it's going to send out this last log index, which is the index of the current last log entry, and also this last log term. So the term of my last log entry. So basically, all the information about the last log entry. We send this out because we want the other servers to look at what our last log entry look like, and to make sure that they only elect us if our log is at least as up to date as theirs. So one example, let's just do this together. Let's just assume that we are the current state machine. We are the green one. And this is what's available on our machine. As you can see, our term is 3. Our candidate ID is 2. Our log index is 3, and term is 1. So the candidate who are requesting a vote from us has these kind of information. It has a term that is smaller than our current term, and it has a different candidate ID, which is expected, and it has a last log index of 3, and log term is 1. So in this case, we choose not to vote for this candidate. So we reject this vote. Why? Because as you can see, it has a smaller term number than ours, right? So that means we, as the current state machine, has been through more elections compared to the candidate. So that means we probably have a more accurate and more up-to-date log. So now we do not vote for this candidate as it's not qualified. So let's do some quiz together. Another example, again, we are the green machine. So how do we, do we vote for the candidate or not? Let's take a look at together. Now we have the same term number. We have different candidate IDs, which is expected. Now our last log index is 4, and the candidate has a last log index of 3. We have the same last log number. So in this case, do we vote or not? If you pause the video and think about it. So, well, okay, so in this case, we decided to reject the vote, right? Because now our current state machine has a longer log index. That means our log is longer than the candidate's log. And in this case, we definitely will not vote for this candidate because we want to guarantee whoever I vote for has a longer log, at least as long as mine, right? So we reject the vote for don't vote for the candidate. And now this is another example. So again, we have the same term, we have different IDs, and then we have the last log entry, which is 5. The candidate has 5, and then I have, as the current state machine, we have the last log index as 4, and then we have the same term. So in this case, do you think we should vote or we should not vote? So in this case, we want to vote for this candidate, right? Because we can tell that the candidate log is longer because it has a longer log entry. It has the last index of this log entry is 5 compared to us, which is shorter. So now we can guarantee that the entry of the candidate is longer, and we can go ahead and vote for the candidate. So this is how you guarantee log consistency during leader election. Now, let's take a look at how to guarantee log consistency during log replication, and how do we repair inconsistencies. Okay, so we check inconsistency when we send this append entry RPC. So remember, during log replication phase, the second phase after we have a leader, we send out this append entry RPC when the leader wants the other followers to also append entry to their own log. So now the append entry RPC has the following information. It has all of the information about the current entry. That means if you take a look at the example on the right, so the append entry RPC has the index of the last entry, the term of the last entry, and the command of the last log entry. And it also has some information about the preceding entry. It has the index and the term of the preceding entry. So let's take a look at how those information are used. During log replication, the goal is that the leader wants the followers to append an entry to its own log, to the followers log. So now, if you take a look at this example, the leader wants the follower, server 0 wants server 1 to append entry 5 to its own log. So now it's going to send an append entry RPC that has all of these information to server 1. And the server 1, what it will does is that it will check if at the log index 4, do I have the same term as the leader's log? So again, for server 1, we're going to check at index 4. Okay, at index 4, we have this entry. And then do I have term 2, which is the same as the leader's term? So in this case, the answer is yes, right? That means we can assume 2 things. One, the command in log entry index 4 are the same. So we have the same entry as the leader. And 2, all the preceding entries before index 4 are exactly the same. So now, after guaranteeing that we have the exact same log as the leader, we can go ahead and append entry 5 to our own log. So what happens if we don't have the same entry? So in this example, again, we're trying to, as a leader 0, we're trying to ask server 1 to append entry 5 to its own log. And now at entry 4, we do not have the same term. So that's inconsistency, right? We have different logs. So what will happen is that the server will go ahead and reject the leader, saying, sorry, I cannot append your entry because we do not have the matching log. So it will reject its append entry request. And now the leader received the request, but it won't simply give up, because we're the leader. We know that we are elected because our log is the best. So we're going to retry. So this is how we're going to retry. We're going to have this entry. So basically, we're going to step back and step into one preceding entry. We're going to treat entry 4 and 5 as the current entry. So we're going to send all of the information in entry 4 and 5. And now we're also going to send a little bit of information of the preceding entry, which is at index 3. We're going to send out the term number of entry index 3. So now we're going to send all of those information to server 1. And the next thing that the server 1 will do, it will receive this append entry request, and it will check at index 3, do I have the same term number? So at index 3, we do have the same term number. So that means we can, again, assume two things. One, at the same entry, in the same index, we have the same command. And also all the preceding entries are the same. So basically, up to index 3, we can guarantee that the server and the leader and the follower has the same log. So now we're just going to copy the leader's log. So we're going to append 4 and 5 to our own log. So this is how you repair inconsistencies during log replication. Okay. So we mentioned this log matching property during log replication. What it means is that for each log entry, so if you look at the example on the right, for each log entry, you compare the index and the term. So for example, server 0 and 1, if you compare at both index 5, do I have the same term number? So for server 0 and 1 at index 5, they both have term number 2. That means you can assume two things. One, the two entries store the same command. Two, all the preceding entries are identical. So that means up to entry 5, up to index 5, everything before this and including index 5 are identical. So that means server 0 and 1 has the exact same log. And now one counter example would be if you take a look at server 2 and server 0. So at index 5, it has term 3. Where compared to server 0, at index 5, it has term 2. So now the term numbers are not the same at the same index. So we'll know that we cannot guarantee that the logs are the same. So this log matching property will prove that they don't have the same entry. So consensus algorithms is very helpful, but also has its own problems, right? So since, as you can see, after we walked through so many examples, there are messages. So we need to send messages to the other servers. So all the components and locates on different parts of the network, and they communicate via message sending. So that means we might have overhead. Well, sorry, we definitely have overhead, and that means we might have duplicate and out of order messages. The overhead is huge, and we also have lots of, we have latencies among the messages, and we could have lost messages. So how do we know that? And also, we could have leader failures. We could also have followers failures. We could also have partitions, which we won't be able to tell why the other server stopped working. And also we could have confidentiality problems. So who has the right to read from our server's log and who has the right to write to the log of our servers? And it's possible to have malicious peers. So we have malicious and misbehaving peers that could abuse our system. One example of this would be the Byzantine generals problem. So this is a story where, okay, you can imagine that two generals are trying to agree on one thing. So they try to decide whether they both want to attack or retreat from a castle. So if they both choose to attack the castle or both choose to retreat from the castle, they win, right? But otherwise, if one chooses retreat, one chooses to attack, they lose. So this seems like a real simple problem to win. But the challenge is that they cannot communicate face-to-face. They communicate through a messenger. So they do not know whether the other server is a traitor or not. So they don't know the other general is a traitor or not. So that just makes everything so much more complicated. So how this applies to distributed system is that we could have Byzantine failures, which means one machine acts normally, but it's a compromised node. But it acts very normally, that it just keeps responding and everything works fine. You just can't tell what's wrong. But instead of sending legit messages, it sends scripts or something malicious that compromise your server and abuse the server this way. So is there any protocol that are Byzantine fault tolerant? Yes, there are Byzantine fault tolerant Paxos and Raft. But the problem with those protocols is that they even have a larger amount of overhead. So some of the takeaways of this talk. In the industry, when you try to implement consensus algorithms, well, the first thing is try not to do that. Basically, when you try to implement it, you should take a step back and think about, is this necessary for me to implement one starting from scratch? So if your system if you could find a service that has been proven to work correctly and proven to be efficient and to be accurate and to be resilient, then it's better to use the existing service than implementing your own, because understanding consensus algorithms is very different from being able to implement it. There are so many more things that you have to consider, and it's very difficult to test it to make sure that everything works right. So also, another thing you have to think about is, when you do have to implement a consensus algorithms, do you want your system to be resilient against those issues? So it's always a trade-off between reliability and complexity. And you have to not only do you need to think about, is my system resilient against those issues, but you also have to think about, is it worth it to be resilient against those issues? Again, it's a trade-off that you have to think about. And in the academia, when you design the consensus algorithms, not only we need to consider the consistency and correctness and conciseness of the algorithms, we also have to focus on the understandability of the algorithms. We really want people to be able to understand our algorithms, to be able to use it, and to be able to adapt to their own systems. So that concludes my talk. I really appreciate everyone's attention, and thank you so much for having me. And again, happy holidays, everyone. Thank you. Now let me switch back. Stop screen sharing. There we go. Okay. I hope you can see me. Okay.
Okay.
So I will take questions if we have time, or if not, we have.
Maybe for one question, as we have
sure.
another talk. Paxos, you said that we have problems when we have few leaders. How does Paxos solve this problem of leader selection when we have empty elections at the beginning?
Right. So you're talking about multiple leaders at the same time in Paxos?
Who wrote this question? You can.
I wrote the example.
Oh, would we have any problems with, for example, we have just started our distributed system. All of our clients are mistrusting. Mistrustful. We all wait for the leader election. How does Paxos resolve it?
If I understand the question correctly, you're asking so do they do anything before a leader is elected? Is that what?
Yeah. Can you confirm is that or not? It's basically, yeah. From what I understand, if all the kind of leaders are mistrustful, how you pick the leader, I think.
Oh, right. How you pick the leader of Paxos. Okay. So again, remember that we discussed that we have this proposal number, right? So at the beginning, the machines, we don't have a leader yet. So the machines will try to send out this proposal number to the other servers and basically saying, I want to be a leader, I propose a value. And now if the machine that's proposing has the largest proposal number, then it will receive the majority of responses from the other server saying that, yeah, sure, go ahead and propose a value. So you remember that it will receive the promise from the other servers. And now the proposer will know that, okay, I got a majority of servers responding saying that I can go ahead and propose a value. That means it can act as a leader. So again, sorry, one more thing. The proposal number is a concatenation between the server ID and the highest round number. So the server ID guarantees the uniqueness of the proposal number, and the round number is, we keep track of the highest number among the other servers. So basically, whoever has the highest proposal number will be acting as a proposer, basically what we call as a leader. If that explains the question.
Hopefully, yes.
Yeah. I will also post my slides online, or what's the best way for me to share my slides?
Just send me an email and I'll share with everyone.
Okay. I will send you an email. Okay. And thank you, everyone. Enjoy the other talk. Thank you.
Thank you.
Bye.
Bye-bye.